Section 3.4 is going to discuss the chain rule, and it's going to give us a different way to differentiate things. It's going to be a lot nicer than having to do it from the definition, that's for sure. But we can see the need for the chain rule when we start looking at something like this. When we differentiate this, well, if we had it all squared out, differentiating that's pretty easy. When we differentiate this, we're off by a little bit. And that factor that we're off by, if you look at this carefully, we're missing a 3x squared term here. So that's what we're missing. Somehow we missed that, but differentiating it like we would a polynomial, we don't get that 3x squared term, but that's somehow missing. So our goal is to first of all start looking at functions and realizing that they're a composition of functions, that it's really two functions put together. So for instance, right here, you've got an outside function, that's your something to the fourth power, and then you've got an inside function, which is this right there. If you put those two things together, this is f of u, this is u, f of g of x would equal this function. So understanding that these functions are compositions is going to be key to working through this section. Let's start out with this one. What's my outside function for this one? Sine of u. Sine of u. And then the inside function is just this polynomial, 3x squared plus 7. Nice. How about the outside function for the next one? Absolute value. And then the inside function would have to be the tangent of x. So you get your outside and then your inside. How about this next one down here? Outside function. U to the fifth. And then e to the x. This is something I just threw in just to kind of give you a heads up. I think it's going to come in Calc 2. It's not just the sine, it's got this h here. So it's called the hyperbolic sine. So it's something a little wild and different, but it doesn't really matter exactly what this is. We still get the outside and inside functions. Now why does that matter? Well, it helps us out when we differentiate because we can employ something called the chain rule. So I've got the chain rule written here on your handout. Something like this. Mostly, I like to think of it like this. It's the derivative of the outside times the derivative of the inside. So that's kind of this formulation. The derivative of the outside times the derivative of the inside. But it takes a little bit of practice to start seeing these things and getting used to those things. So we're going to do it this way. We're going to start out kind of like this. And this is going back to the notation that Leibniz used. He wrote his derivatives, his differentials like this, dy by dx. This has a lot of advantages in this situation. So for instance, if we were to look back at the one we started this whole mess out with, we had, and I'll just call this example A. I'm just going to replace the example A that we have here. Y equals x cubed plus 7 squared. Let's see if we can't write this in terms of an outside function and an inside function. So our outside function, what's the outside function we see when we first look at this? Yeah, something squared. So f of u is going to be u squared. And the inside function? Yeah, x to the third plus 7. So that's kind of like our u equals our g of x. So if I wanted to, I could put this together as f of g of x would give me this, x cubed plus 7 squared. But let's just write it like this. We're going to have y equals f of u and u equals g of x. So if I wanted to differentiate dy by dx, I could think of it first as differentiating y with respect to u, and then differentiating u with respect to x. So differentiate y with respect to u and u with respect to x. This is the advantage of this notation with Leibniz. What does it look like you could do here? It looks like you could cancel the du's, right? And if you cancel the du's, you'd be left with dy by dx. So that has the right feel to it, that those would cancel and you get the right thing. Now, let's take a look at what each of these would be. If I differentiate this with respect to u, what's the derivative of this with respect to u? 2u. 2u. Nice. And now let's differentiate u with respect to x. So what's the derivative of this with respect to x? Yeah, just 3x squared, right? So 3x squared. Now it feels a little awkward to have a u and an x in this at the same time, right? So let's clean that up a little bit. What was u representing? What did u take the place of? Yeah, u is x to the third plus 7. So this is going to be 2 times x to the third plus 7 times 3x squared. Well, we can distribute this kind of a piece at a time. I'll distribute the 2 here first. That's going to be 2x cubed plus 14 times 3x squared. Maybe I should write that out in front. So the 3x squared here. And guess what? This is exactly what I said we should get when we looked at this earlier. You've got the derivative of the outside, which is this, times the derivative of the inside. Ah, okay, yeah, we were missing, when we initially did this, we were missing that 3x squared factor, but now it's there. And if you distribute that, you get 6x to the fifth plus 42x cubed, or x squared. So wow, that actually worked. Now, I'm not a big fan of splitting it up like this, but I'm hoping that it's going to be an easy transition into thinking of these types of problems as the derivative of the outside times the derivative of the inside. And that's really what you're doing here. When you've got something like capital F of x defined like this here, an outside function and an inside function, you're differentiating the outside times the derivative of the inside. That's the chain rule. That's what you're going to have to build up to. So let's do another one kind of like that. Let's pick on example B, see if we can't take care of things that way. So let me move down to example B. Any comments on example A before I move on to example B? We're okay with this one? Thank you. James, yeah? Okay, good. All right, let's take a look at example B. Example B is going to be y equals e to the 2e to the x. So again, you've got to split this up as an outside function and an inside function. So let's see here. This one's going to be a little on the trickier side. The outside function is e to some power. So y equals some function of u is going to be e to the u. And then the inside function is u is going to equal g of x. What's g of x going to be in this case? Yeah, thank you, Christian. 2e to the x. Great, so you got your outside function and then your inside function. If we were to differentiate this, then dy by du, or excuse me, dy by dx, see if you can't fill in these two things here for yourself. What would it be? You're going to differentiate y with respect to this variable, and then you can differentiate this variable with respect to x. So see if you can't fill in those two things. So what would those two things look like? What should I be writing there? Yeah, du. You're going to differentiate y with respect to this variable. Y is defined in terms of u. And then you're going to differentiate this variable, u, with respect to what it's defined in, du by dx. And these things, boy, they certainly look like they cancel each other out, right? That's the way they should. It's by design here. So let's take a look here. dy by du. When you differentiate e to the u, what do you get? E to the u. Nice. How about if we differentiate 2e to the x? Yeah, 2e to the x. The 2 you ignore. You differentiate e to the x, you get e to the x. 2e to the x. The last thing to do is to plug back in for u. So it's going to be e to the 2e to the x times 2e to the x. Kind of messy, maybe a little uncomfortable. Some of you are probably looking at like, oh, gee, I'd really like to simplify things here a little bit. If you did really want to simplify things a little bit, you could bring the 2 out front, and then you've got these two things that have the same base. What happens to things when you have the same base? What do you do with their exponents? Add. So 2e to the x plus x. That'd be another way to write it if you're desperate to try and write it a little bit simpler. That would be how it would look. Okay. So that's one way of doing these things. And, you know, when you're starting out, it's not a bad way to do these things. But I'm hoping that you can start moving beyond the need to write things out and do it like this. If that's what works for you, great. I'm not going to be grading you down if you take a little bit more time and get it right. There's nothing wrong with that at all. But hopefully, you're going to start being able to look at things like example C and just do it cold. So let's take, starting with example C, let's try and just do the derivative of the outside times the derivative of the inside. Example C, y equals x to the 4th plus 3x squared minus 8 to the 6th power. Now you can be thankful we have the chain rule here. If we didn't, you'd have to multiply this by itself 6 times, collect all the like terms. I can't even imagine how much work that would be to do it that way. And there's no Pascal's triangle that's here because Pascal's triangle only works for, you know, binomials. So it'd just be an enormous amount of work if you had to do it that way. But somebody help me out here. Antonio, what's the outside function in this one? Yeah, something to the 6th power, all right? So when we differentiate this, it's going to be the derivative of the outside, so that 6 is going to come out in front. And what's going to happen to the exponent? Yeah, you subtract 1. Yeah, so you get something to the 5th power times the derivative of the inside. So d by dx says, oh, I'm going to take the derivative of the inside. So this is the derivative of the outside. Jameson, what's the derivative of the inside?
4x cubed plus 6x.
Nice, nice. X to the 4th plus 3x squared minus 8 to the 5th times 4x cubed plus 6x. And that's about it. You can't really do much more with that unless you wanted to raise that to the 5th power. Yes, sir?
Where do you get the 5th power from?
Oh, this was a 6 here, right? So when we looked at this and we differentiate the outside function is something to the 6th power, so the 6 comes out in front and subtract 1 from the exponent. All right? Appreciate the question, though. Thanks, Ethan. Yes?
This might be a silly question.
No.
So we can't
4 plus 6. Technically, we could extract the 2 out of that and then take that 2.
Yeah, we could take out a greatest common factor here. So if you wanted to, let me write that out in front. Cubed plus 6x, x to the 4th plus 3x squared minus 8 to the 5th. Yeah, and if you wanted to, you could factor out a 2 here. So taking out the 2 times 6 would be a 12. And that's going to leave behind 2x cubed plus 3x. I could have taken out an x too, I guess. And then x to the 4th plus 3x squared minus 8 raised to the 5th. I probably should have taken out an x. What you're going to have to eventually do with these kinds of problems is solve them. You're going to have to set them equal to 0 and figure out where they cross the x-axis, where they're increasing, where they're decreasing, etc. Now, in a problem like this, my goal is really just for you to show me that you know the chain rule. So I'd be happy with this. If you were going to factor this and clean it up a little bit, then I guess I'd be happy with this one as well. So if you did want to clean it up, eventually you are going to need to clean these things up. All right. Eventually this is just going to be one step in a different process. Mage? You know, I'm not going to be doing U substitutions after this. I mean, we did a couple just so that you see the notation. There's going to be some problems in WebAssign that are going to work like that and look like that, so you'll have to play with it so you've seen it. But is it something I'm going to test? No. No. For us, what you really need to be able to do is look at this and in your mind realize that my outside function is f of u equals u to the 6. My inside function is g of x is x to the 4th plus 3x squared minus 8. So yeah, that's mostly what I would expect here, is that you're doing this part but in your head. Okay? Good? All right. Let's keep working. Example D, kind of a nice little change of pace here. So let's do that one maybe here. Example D gives us h of x is the square root of 3 plus 2 times f of x. And they tell us that f of 3 equals 3 and f prime of 3 equals 5. They want us to find h prime of 3. So, okay. Let's rewrite this function here first, because we don't have a rule for differentiating square roots. But we can rewrite that to something that we do have a rule for. Yeah, thanks. Appreciate that, Ethan. Something 1/2. So this is going to be h of x is 3 plus 2 times f of x to the 1/2. Now it's set up to use the chain rule, right? You've got an outside function and an inside function. So what's the outside function in this one? Something to the 1/2 power. So if you're differentiating something to the 1/2 power, what's that going to look like? Well, let's just do it with the radical notation, or with exponent stuff that we replaced here. Your outside function is something to a power. When you differentiate something to a power, remember you're going to subtract 1 from the exponent and or multiply by the exponent, subtract 1 from the exponent. So it's going to be 1/2 here, and then negative 1/2 here. 3 plus 2 times f of x raised to the negative 1/2 times the derivative of the inside. Now this is where it gets a little bit tricky / interesting, but I think we can handle it. Arlie, help me out with the derivative of the inside. What's the derivative of 3? Now 2 is a constant, so I can kind of ignore that. If I differentiate f of x, it's just f prime of x, right? So I'll multiply this by that constant times the derivative of this function, 2 times f prime of x. Do I know what f prime of x is? I don't know what it is, but I do know what its value is at 3. So if I wanted to find, say, for instance, h of 3, or h prime of 3, let's do that. H prime of 3 is going to be, and if you're wondering why I didn't clean this up a little bit, I can. I mean, the 2 and the 1/2 cancel each other out. That's fine. But I guess maybe I should clean this up a little bit. 1/2 times that. The 2 here and the 1/2 here are going to cancel out. What happens with something with a negative exponent? It goes into the denominator, right? So the 2's cancel each other out. I'll have f prime of x divided by 3 plus 2 times f of x raised to the 1/2 power. That's going to be a cleaned up version of my derivative. And that should help me out when I try and figure out the rest of this. So h of 3, that's going to put a 3 in here and a 3 in here. But we've got those values. F prime of 3 was 5. So I'll put a 5 in there. What about f of 3? F of 3 was 3, so I'm going to have a 3 down here. So let's put that in as well. So I'll have 3 plus 2 times 3 raised to the 1/2 power. A lot of substitution stuff here, but nothing too bad, I don't think. Are we together with where I put all these things in from? All right, some nice nods. I appreciate that. So it's going to be 5 over the square root of 9. Square root of 9 is 3. So there's your answer, 5/3. Christian, too much in one step, maybe?
No, I figured that out. I'm trying to figure out what happened to the 1/2.
The 1/2 times the 2, those
Oh,
cancel
got it.
each other out. So appreciate the question there. Thank you. Anything else that looks a little iffy on this one? Now that's kind of a nice lead into another type of problem that you might see on the homework, which is one that involves just some tables. And then we'll get into the other ones, like F, G, H, and I. Work on some of those. Let's just do one of these. I don't want to get bogged down in the whole table, but if you're a little unsure about some of these things, then maybe we can do another one. So let's see. We want to find h prime of 1. So that's our goal here, is to find h prime of 1. And h of x is f of g of x. H of x equals f of g of x. So h prime, this is just your chain rule again. It's the derivative of the outside times the derivative of the inside. James, what would it look like for this one? Derivative of the outside would be f prime of g of x. What's the derivative of the inside? That's the inside. What's the derivative of the inside? What should I write? Yeah, thank you. G prime of x. So there's your derivative of the outside times the derivative of the inside. And the problem asks us for h prime of 1. So let's put in the 1 everywhere we need it. So that's going to be a 1 here, and a 1 here, and a 1 here. So it's going to take a little bit of work there. Are we okay with the way I filled this in, though? H prime of x. See if you can't chase down the rest of these values and simplify this, give me a product. I'll kind of walk around, help out a little bit. If you're watching this at home later, then there we go.
And then f prime of 2 is 5.
Oh, I see, I see. So you need to find G1 first. So that's F prime of 2.
So you want to use the table that's up there.
Don't forget your
So
prime.
you should have right down what I have there for each one. We'll use the table to figure out the rest of these things.
Times G prime of 1.
Nice, nice. So we can do better than this one.
This is G prime. Oh, sorry.
Yeah, so you just.
All right.
No, this
And
one
then you
is
got
6.
the G prime value, so you just find G prime of 1 in the table, which is 6.
Put a one there. So it's not the one.
It's just G. Well, it doesn't matter because it's 6 on G, but it's just.
Oh, you do, oh, you do the next one. So, I mean,
G prime 1 is 2, that's
it's gonna
right.
work out similar, but you're just gonna have different numbers. Yeah, you got your split.
2 so it'd be f prime of 2. F prime of 2 is 5. So that's
That
right.
makes sense. Like,
Awesome.
Is that G prime of 1?
yeah.
And then it's
So
5
G
times
prime
6, and that's
Yeah,
right.
1.
You get 6, right? Not 2. And then G of 1.
No offense. I don't. Oh, I thought you said. No.
Okay, so let's look through at these. First things first, work with the inside out. G of 1 is going to be 2, so I'll put in a 2 here. G prime of 1 is going to be 6, so I'll put in a 6 here. And then I can work with F prime of 2. F prime of 2 is going to be 5, so I'll end up with that much is the 5 times 6 is 30. Nice. Nice. So basically asking you to apply the chain rule there. Okay. Looking good on those. Do we need to do another one like that, or are we okay there? All right. Placid, docile looks seem to suggest that we can go on. If you have some questions, though, please ask. Let's move on to example F. Example F is going to wake you up a little bit because it's going to be a little more challenging. Y equals x squared plus 2 over x squared minus 2 raised to the 8th power. Wow. This one would be a real nightmare without the chain rule. It just would. So let's start out. What's my outside function in this one? What's the first thing you see when you're looking at this? Something to the 8th power. How do you differentiate something to the 8th power? Yeah, so if you had u to the 8th, then dy by du would equal 8u to the 7th. So, all right, let's work on that part. So dy by dx is going to be 8 times x squared plus 2 over x squared minus 2 raised to the 7th power. But we're not done. Please don't stop here. You're missing the chain rule. What else do I have to do? Times the derivative of the inside. So that's d by dx means we're going to take the derivative of the inside, x squared plus 2 over x squared minus 2. Ooh. What rule do we have to use? Yeah, you got to use the quotient rule. Everyone's favorite. Even your instructor couldn't really easily avoid using the quotient rule on this one. So, not a bad idea to practice the quotient rule. 8x squared plus 2 over x squared minus 2 raised to the 7th power. Quotient rule. Go at it. Have fun. First one with the right answer gets to share it on Instagram with all your friends. Okay, so your first pass at the derivative should look like this. You start with the square of the denominator, and then use the denominator again. So you're using the denominator twice before you do any differentiating. Denominator times the derivative of the numerator, which is 2x, minus the numerator times the derivative of the denominator, which is also 2x. Now, if you're going to clean this up, and I do hope and suggest that you do, there's a lot of things you can do to clean this up. But there's something that caught my eye about this. And that is I had a greatest common factor here, right? 2x. So I'm actually going to start by factoring out that greatest common factor, 2x. It's going to leave behind an x minus 2. So an x minus 2, or x squared minus 2, minus this other term, x squared plus 2x. Or excuse me, x squared plus 2, not 2x. So, factoring that out actually kind of works pretty nice. X squared plus 2. Can anyone see how this is going to simplify when I'm all done? Think through in your head carefully. You've got to distribute that negative to both terms. I think I heard somebody whisper it. Yeah, a minus 4. And that should be to the 7th power still. So it's going to be 2x times a minus 4. Wow, that cleaned up pretty nice in the numerator. So overall, a minus 4 times a negative 2, or times a 2x is going to be a negative 8x times x. Let's just write that all out front. Minus 64x times, let's see, let's see. You know what? Let me do it over here. Well, I'll write it this way first. X squared plus 2 over x squared minus 2 raised to the 7th. But I still have this thing squared in the denominator. So I have 1 times that, x squared minus 2. And I'm sorry I'm kind of running out of room there. But if you really wanted to clean this up a little bit more, negative 64x, you've got 7 of these in the numerator, x squared plus 2 to the 7th. You got a total of 9 of them. 2 and 7 gives you x squared minus 2 to the 9th power. I'm not sure I'm going to be that demanding in terms of cleaning things up. If you want to just write it as, you know, negative 64x over x squared minus 2 squared times x squared plus 2 over x squared minus 2 to the 7th, I'd be fine with that. You know, I'm not going to ask you to split these things up and be too crazy about it. So either of these would be fine. Just clean it up a little bit. All right? Don't just give me a blob like this. I would expect that you would at least clean up this stuff in parentheses. Nice. Nice. Okay, that was a tougher one. Notice the mood in the class seems like really somber now. Yes?
I don't know, it's like the stuff where
Are you okay with the minus 4 here?
no.
Okay. So when you distribute this negative, you're going to get a negative x squared minus 2. X squared and the minus x squared, those are going to cancel then, right? The minus 2 and the minus 2 give you a minus 4. So that's where we get the minus 4. Good? All right. Anything else on this one? Happy to help out. Okay. Let's try. Let's try example G. So example G. Y equals 6 over 1 plus e to the negative x. As it stands, what rule would you have to use in order to differentiate this? Quotient rule. Ugh. I don't think there's a lot of people in this classroom, I don't even need to take a poll, who are real fans of the quotient rule. Quotient rule is kind of a pain. So is there a different way I could rewrite this? If you rewrite it as something to the negative first power, now I don't have to use a quotient rule. And if all you need is just a derivative, it might be the way to go. dy by dx. What's the derivative of a constant? It's just 0. We kind of ignore that. We're just going to multiply 6 times the derivative of this function. So that's negative 1 out in front, negative 1 minus 1, because you got to subtract 1 from the exponent. Times the derivative of the inside. So we're going to take the derivative of the inside, 1 plus e to the negative x. So this gives me a 6, 1 plus e to the negative x to the negative 2 times the derivative of this function. Now the derivative of this is 1, or excuse me, the derivative of this is 0. So then we have to differentiate e to the negative x. And unfortunately, that means you have to use a chain rule again. Let me give you a little shortcut on this, though. help you out if you run into these problems. And it's really based on the chain rule. If you're differentiating e to the u with respect to x, so d by dx of e to some function, doesn't matter what it is, it's going to be e to that function times the derivative of the exponent. So basically you're just going to take whatever this is and multiply by the derivative of the exponent. So in our case, our exponent is e to the negative x. What's the derivative of negative x going to be with respect to x? Negative 1. So what you'll end up with is negative 1 e to the negative x. Your exponent is negative x. If you differentiate that with respect to x, you get negative 1. So negative 1 this times negative 1, or put the negative 1 out front. Let's clean this up at least a little bit. Negative 6 times negative 1 is going to be a positive 6. This term with a negative exponent can go into the denominator. This term will stay up in the numerator. So it's going to be 6 e to the negative x over 1 plus e to the negative x squared. Whew. A lot of manipulation on that one.
Can you leave the negative x's in?
The negative exponents don't bother me too much.
Okay.
You could clean this up a little bit if you wanted to. You could bring this down to the denominator and write it as 6 e to the x times 1 plus e to the negative x squared. But if you wanted to get rid of that e to the negative x completely, you'd have to square this out and then do a lot more work. So I'd probably leave it like this. To me, it's not worth the extra work. You could do it. I just don't really see the benefit, but I appreciate the question. So yeah, a good final form would either be this one here or this one here. Both of those are good final forms for this answer. Yes?
Is it, let's say we started from the beginning and we did 6 times e, or 6 times like the x root of e, is it still solvable using the chain rule, or no?
One more time on the rewrite of that. What would?
Like if we were given an equation that y also equals 6 times the x root of e.
It's not. That wouldn't be the proper interpretation of that. It's not. Yeah, it's not really the x root of e. Well, let's see.
Just because it's an x, but like,
Yeah, but no, I don't think you can rewrite that using square roots and things like that. So, no, good try. Don't think you could rewrite that one with square roots.
because it turns the e into an inside value, but yeah, I was just curious because it's not.
You got me curious on that one. I don't think I would go that route though. Yeah, yeah. I'll have to think about that one a little bit more. Appreciate the question though. Thank you. Let's do example I. I know we're going to skip example G. Want to kind of finish things up here, and then we'll finish with example J, which is a look back at the Witch of Agnesi. Example I. So we've got y equals sine of x squared, and you're asked to find y prime and y double prime. What's y double prime anyways? Yeah, the derivative of the derivative or the second derivative. So let's start with the first one, y prime, or alternative notation for that is dy by dx, the Leibniz notation. And looking at this one, what's our outside function?
Sine.
Sine. All right. John, what's the derivative of sine? Cosine. So that's cosine of x squared times derivative of the inside. Rahana, derivative of the inside. What's its derivative? 2x. Nice. Nice. So I'll clean that up as 2 times x times cosine of x squared. Great. Let's copy that onto the next page here for myself. So 7, 8. It's going to be a busy note day. So we got y prime equals 2x cosine of x squared. What do we have to do when we differentiate this one? Ah, well done. Thank you. The product rule. All right. So that's going to be your f. That's going to be your g. You're going to have to use the product rule to differentiate this one. Christian, you look unhappy about that. It's like this problem's tough enough, and now you got to throw the product rule in on top of it. So to soften the blow, let me tell you in Spanish, sí. Right. Yes, you have to use the product rule. So let's remind ourselves of a couple things here real quick. You've got f, which is 2x, and g, which is cosine of x squared. Let's figure out both of these. Christian, help me out. I'll give you the softball first. What's the derivative of 2x?
2.
Yeah, just 2. Now when you differentiate the second one, when you differentiate g, what rule do we have to use to differentiate g? Ah, great questions. Not the product. You don't have cosine times x. The chain rule. You've got an outside function and an inside function. Believe me, that's not the first time I've ever gotten people wanting to use a product rule here. It's not two functions that are multiplying each other. So don't feel bad if that was your inclination. So we need to start with derivative of the outside.
Negative sine.
Nice. Derivative of the outside is negative sine of x squared. So the derivative of the outside of the inside times the derivative of the inside. 2x. Or if I clean that up, negative 2x sine of x squared. Now a reminder here, f prime, or f times g prime is f prime g plus g prime f. So it's just a matter of some cross multiplication of these two things. I'll start here. F prime times g plus g prime times f. Let's see. There's not much cleaning up that we can do here. You could factor out a 2 if you wanted to. I don't really care. Where's an x squared here? Negative 4. Oh yeah, x times x would be an x squared. Thank you. Yep. Nice. Nice. So that's f double prime. Did I talk about the third derivative at all? Here's kind of a little FYI. If you want to insult somebody in kind of a highbrow way. So when you're working with functions in particular, sometimes you work with, say, y equals s of t. S of t is going to be your displacement or your location. And when you change your location, y prime of t, you get, well, changing your position, you're moving. So you have a velocity function. what happens when you change your velocity? What are you doing to change your velocity? What's that?
Acceleration?
Yeah, acceleration. So the second derivative of your position is acceleration. But here's the funny part. Here's the highbrow way to insult somebody. If you change how you accelerate, if you accelerate quickly and then slowly and then quickly and slowly, what would happen to the passenger in your car? They'd be lurching backwards and forwards, backwards and forwards. They're getting jerked around. So quite literally, the third derivative is the jerk function. So if you want to insult somebody, you can call them a third derivative. Not too many people are going to catch on to that. You'd probably be safe in most situations. Yes, sir.
So how did you know, the difference, to recognize a function on whether you should use the chain rule or the product rule?
Well, we actually used both in this one, didn't we? And this is the way I broke it down. I'm like, all right, you've got this function times this function. So that's the product rule. So right there we had to use the product rule. And because this function is really the composition of two functions, we had to use the chain rule when we differentiated that one. So it was a combination of both of those. So you got a twofer on this one. You got to use the product rule and the chain rule. So you're just going to have to look at these functions and decide, how they're broken up. It's just something that's going to take some practice. Just like anything that you're good at, you want to be good at something, you practice. And unfortunately, there's no pill that we can take to just be good at these things. It's going to take practice. It might not look that way to the untrained eye. It's like, well, wait a minute, this feels weird. But we're going to do a lot of these problems. We're going to keep on differentiating outside and inside functions. So I hope that you start to build a feel for it. I think that if you do the homework diligently, you probably should. But I don't have a quick, easy answer for you. I mean, you're just going to have to look carefully at these functions and realize, okay, it's these two functions, and this one is really the composition of functions. That's why we started out with, practicing outside and inside functions so that you can start to recognize that. And when you see the outside and inside function, that's when you know you got to use the chain rule. So if you can write something as a function of u and then u is a function of something else, then yeah, that's where you use the chain rule. Okay? All right. Appreciate that. Let's do the last one here, which is example J. This is going back to the Witch of Agnesi problem. Maria Agnesi. Of course, her name in that was because of a mistranslation, but it's just kind of stuck. As it stands, how would we have to differentiate this? What rule would we have to use? Quotient rule. All right? Quotient rule is not a whole lot of fun always. Sometimes you need to use it, and if you need to use it, that's great. But if you wanted to avoid the quotient rule in this one, what would you do? How would you rewrite it? 1 plus x squared to the negative 1. Now you've got an outside and inside function again. So we can differentiate this one. So what's our outside function? Yeah, something to the negative first power, right? You've got something to a negative first power. Maybe it helps out to write it down. So we've got u equals f of u is u to the negative first power. And then, actually maybe I should write y equals f of u. And then u equals what? What's my inside function? Mage? What would the inside part be here? That'd be the derivative of this. I mean, so before we get there, 1 plus x squared. But you're right, it's going to be a 2x. So you've got derivative of the outside of the inside times derivative of the inside. So that's going to be a -1 and up to the -2 power, right? 1 plus x squared raised to the -2 power. Derivative of the outside times the derivative of the inside. Maybe this is what you gave me just a minute ago. Derivative of the inside is 2x. That -2 only applies to this power here, or this term right here. So this is going to leave the -2x in the numerator over 1 plus x squared squared. Nice. That's a lot faster than it was when we differentiated with the quotient rule. All right, it's much cleaner. There is still a little bit more work to do. We want to find the equation of the tangent line at x equal -1. So at x equal -1, first of all, let's figure out what the point is on that. If x equals -1, what's my y coordinate? Yeah, 1 over -1 squared plus 1 gives me 1/2. So there's my point, -1 and 1/2. What else do I need in order to find the tangent line? Slope, yeah. Great. How am I going to find the slope? Yeah, plug in -1 into which one of these? F prime. So the slope of the tangent line is going to equal f prime at -1. So let's plug in that -1. So yeah, let me do it in green here. -1, -1, -1. So it's going to be 2. Let's see, it's going to be 2 over 4. So it's going to be 1/2, right? So we get a slope of 1/2 for the tangent line. And now it's just a matter of y minus y1 equals m times x minus x1. Y minus y1 equals m times x minus x1. And we've got all we need. It's going to be y minus 1/2 equals 1/2 times x minus -1. If we distribute that, that's going to be a +1. We'll end up with another half from over here. So we get y equals 1/2 x plus 1. Whew. Is it worth a minute to check that on our graphing calculators, or are we confident? You guys confident? All right, cool. Me too then. All right, that's it for section 3.4.